There is a stretch of the Trans-Canada Highway west of Sudbury, Ontario, where the landscape looks like every other stretch of the highway in the region. Jack pine, gray rock cuts, a roadside diner, a freight line, a river too shallow to bother naming if you did not already know it was there. Ordinary, empty, completely unremarkable. Except in the hills north of that road sits a basin roughly 60 kilometers long and 25 kilometers wide that has produced more nickel and copper than almost any other piece of ground on Earth. More than the Klondike produced gold, more than the Fraser River by a comfortable margin, than every creek, gulch, and placer pit of the Caribou Gold Rush put together. And it is still producing. Right now, this morning, in 2026, under lights, on a shift schedule that has not stopped in over a century. That is not the strange part. The strange part is that for generations, people walked directly over it. Indigenous travelers, fur traders, and early survey crews followed the canoe routes straight past the rim of it, chasing beaver pelts and timber, and nobody on those routes noticed what the rock actually was, because the wealth under their boots was misread, not buried beyond reach, not hidden behind an impassable ridge. Misread, locked in gray norite and shattered breccia in a structure so large and so old that its true origin sounded like fantasy until modern impact geology proved it. Nobody understood what created it until 1964, and when geologists finally confirmed the truth, they did not do it by finding a volcano. They did it by finding shatter cones in the rock, signatures left behind by an asteroid impact nearly 2 billion years ago. So, how does one of the richest mineral structures on the continent stay misunderstood for 80 years in one of the most heavily surveyed provinces in the country? And what does it actually add up to, now that someone finally understands the geometry of a giant impact? Across these 5 parts, we will trace the hidden geographical anomalies of Canada, counting down through 13 distinct provincial and territorial sites, from the shifting crescent of Sable Island off Nova Scotia to the massive, drowned communities beneath the St. Lawrence Seaway. Northern Ontario was never supposed to be defined by a cosmic collision. Northern Ontario was defined by timber and railway lines, and it knew exactly when its mining story began. 1883, during the construction of the Canadian Pacific Railway, when a blasting crew cut through an outcrop near Sudbury and exposed a heavy seam of copper and nickel ore. For decades, that discovery built towns out of nothing, funded infrastructure across the province, and gave the region an identity so complete the early reports reads like a mineral inventory. Nickel in the hills. Gold, if you wanted gold, was thousands of kilometers west in the Yukon. And so, the Canadian Shield was walked. Every outcrop, every lakeshore, every ridge that showed a stain of rust was staked, sampled, and argued over by prospectors who did this for a living and were good at it. By 1910, the assumption was simple. If there were a major geological structure here, it was an ancient volcano. The assumption was reasonable. It was also built on a framework that had been used for generations. Every early model of Canadian Shield geology depended on terrestrial processes, volcanism, slow tectonic folding, and magmatic intrusion. Geologists looked at the ring of dark rock around Sudbury and saw an ancient volcanic basin. A prospector could hold a chunk of heavy ore in his hand and know it held nickel, but the giant circular geometry of the basin itself remained misexplained. Men stood on top of what is now known to be a 2-billion-year-old crater, hundreds of kilometers wide at its creation, assuming they were standing on the rim of a collapsed volcanic vent. The early theory seemed solid, but as deep drilling advanced, the volcanic model began to break down. The rocks inside the rim did not match typical volcanic flows. They were full of crushed, shocked fragments that required energy levels no earthbound volcano could generate. Yet, for decades, official reports from the Geological Survey of Canada and provincial bureaus kept referencing volcanic activity because the alternative, that a mountain-sized rock had struck the Canadian Shield from space, was simply not how geologists were trained to think about economic ore bodies. It took until the mid-20th century for scientists like Robert Dietz to point to shatter cones, distinctive conical fracture patterns formed only by high-intensity shock waves, and demonstrate that the Sudbury Basin was an impact structure. That shift in understanding transformed how geologists mapped the entire region. The nickel was not brought up by a standard volcano. It was pooled at the base of a massive melt sheet formed when the impact melted the Earth's crust, concentrating heavy metals into the fractures of the shattered rock beneath. The Misread stone was finally correctly filed, and as we look across Canada's vast geography, this pattern repeats again and again. Landscape features that were mapped, walked over, and recorded, yet whose true scale and origin remained hidden in plain sight right up until a new frame of reference replaced the old assumptions. To understand how a geological feature as colossal as the Sudbury Basin could remain misread for nearly a century, one has to travel back roughly 1.85 billion years to the Paleo-Proterozoic era. At that time, the ancient continental core that now forms the Canadian Shield was a very different landmass. A meteorite or comet nucleus, estimated by geophysicists to have been between 10 and 15 kilometers in diameter, slammed into the Earth's crust at a velocity exceeding 20 kilometers per second. The force of that collision released energy calculated at several billion times the yield of a standard nuclear weapon. It was not a gentle intrusion of magma. It was an instantaneous, violent reshaping of the planet's surface. The kinetic energy transformed into heat on impact, instantly vaporizing the bolide itself and excavating a crater roughly 150 to 200 kilometers across. The underlying crust melted, creating a massive lake of liquid rock hundreds of meters deep, what geologists call the Sudbury Igneous Complex. As this superheated melt sheet slowly cooled over thousands of years, heavy metallic elements separated from the liquid stone. Rich concentrations of nickel, copper, platinum, and cobalt settled toward the base of the sheet, pooling in pre-existing fractures and depressions in the shattered floor of the basin. Over the next 2 billion years, mountain building events, immense pressure, and extensive erosion wore down the top layers, leaving behind the elliptical oval ring visible today. When European surveyors and prospectors first arrived in the region during the 19th century, they had no conceptual model for meteorite impacts of this scale. The prevailing scientific wisdom, championed by early figures at the Geological Survey of Canada, attributed all large ring-like structures in crystalline shield rock to ancient collapsed volcanoes. This was a logical conclusion for the era. Volcanic activity was well understood, documented across the world, and known to bring mineralized fluids to the surface. Meteorite craters were thought to be small, rare, and confined to modern surface pockmarks like those observed on the Moon. Thus, when surveyor William Logan and his contemporaries examined the dark, coarse-grained norite and breccia surrounding Sudbury, they mapped it as a volcanic complex. The land was formally assigned to timber licenses and later, following the 1883 railway discovery, to mining claims. Thousands of workers moved into the area to mine what they believed was a classic volcanic intrusive complex. For decades, the official record, preserved in provincial government survey reports and university lecture halls, maintained this volcanic classification. Prospectors mapped new ore zones by looking for features associated with volcanic vents and magmatic pipes. Millions of tons of high-grade nickel and copper were extracted under a geological assumption that was fundamentally incorrect. The true mechanics of the site remained obscured not because the evidence was missing, but because scientists were looking through a narrow theoretical lens. It was only in the mid-20th century, as space exploration and nuclear testing forced geologists to study hypervelocity shock metamorphism, that the volcanic consensus began to fall apart. Scientists noticed that the shattered rock around the basin contained unique microscopic features, planar deformation features in quartz grains, and distinct cone-shaped fracture structures known as shatter cones. These features do not form in volcanic eruptions. They require the extreme, sudden pressure of a cosmic impact. When researcher Robert Dietz identified shatter cones near Sudbury in 1964, the long-standing volcanic model collapsed. What had been taught as a terrestrial volcanic basin for 80 years was revealed to be the eroded root of one of the oldest and largest impact structures on Earth. Yet, solving the mystery of Sudbury's origin only raised broader questions about the rest of the continent's geology. If an impact structure of this magnitude could hide in plain sight under the guise of an ordinary volcano, what other massive, misidentified anomalies were waiting to be recognized across the vast expanse of the Canadian Shield? The shift in how geologists viewed the Sudbury Basin was not brought about by a single lucky find, but by a series of precise analytical breakthroughs that forced researchers to re-examine the physical evidence under entirely new paradigms. For nearly 80 years, field geologists had recorded the oddities of Sudbury's rock formations in notebooks and maps without connecting them to an extraterrestrial event. The turn began in the 1950s and 1960s, driven by an international effort to identify hypervelocity impact structures on Earth, led in large part by scientists at the Dominion Observatory in Ottawa and the Geological Survey of Canada. Researchers like Carlisle Smith Beals began systematic reviews of aerial photographs and gravity maps, searching the Canadian Shield for circular anomalies that did not fit standard volcanic or tectonic models. But proving an impact required physical proof that only high-pressure shock physics could provide. The turning point arrived when geologists examined shatter cones, striated conical fracture surfaces in the quartzites and greywax surrounding the basin. Shatter cones are created only when a high-intensity shock wave, traveling at several kilometers per second, passes through solid rock. Volcanic explosions simply do not produce the pressures necessary to generate these distinct fracture patterns, which require pressures exceeding 2 gigapascals. When Robert Dietz mapped the orientations of these shatter cones around Sudbury in 1964, he found that their apexes consistently pointed upward and inward toward the center of the basin. When the structural tilting of the surrounding rock strata was mathematically undone, the cones pointed toward a single point high above the present ground level, the exact point where an exploding bolide would have deposited its energy. Further proof came from the microscopic level using thin-section petrography. Petrographic examination of quartz and feldspar grains from drill cores retrieved from deep inside the basin revealed planar deformation features, sets of extremely narrow, parallel deformation lines formed within crystal lattices under shock pressures that no volcanic or metamorphic process on Earth can replicate. Later, argon-argon isotope dating and uranium-lead geochronology on zircon grains extracted from the melt sheet precisely dated the impact event to 1.85 billion years ago, confirming that the melt sheet and the shattered breccia below formed simultaneously in a single catastrophic instant. Airborne electromagnetic surveys and reflection seismology conducted across northern Ontario in subsequent decades added further depth to this model, mapping the deep asymmetrical root of the basin miles beneath the surface and proving that subsequent mountain-building forces had squeezed and deformed what was originally a circular crater. What had been viewed for generations as a conventional volcanic basin holding rich magmatic mineral deposits was fundamentally redefined as a gigantic, impact-generated melt pool that trapped and concentrated heavy metals as it solidified. The proof was absolute, verified by multiple independent lines of physical evidence, and it completely altered how geologists evaluate deep-time anomalies across the Canadian landmass. But understanding how an ancient collision created one of the richest mining districts on Earth is only part of the story, because the physical legacy of this transformed landscape extends far beyond the rock core into the modern era. Today, the consequences of that ancient impact shaping modern geography are measured in hundreds of billions of dollars, vast underground networks, and continuous environmental management across the city of Greater Sudbury. Over more than a century of mining, the Sudbury Basin has produced over 8 million tons of nickel, alongside millions of tons of copper, cobalt, silver, and platinum group metals. In terms of lifetime mineral value, total production from the basin is estimated by Natural Resources Canada and the Ontario Geological Survey to exceed 150 billion Canadian dollars. To put that figure in context, it represents a substantial share of the historical mineral wealth generated across the entire province of Ontario. But that wealth came with a profound structural transformation of the local terrain. The extraction of ore along the outer rim of the impact structure has required the excavation of dozens of open-pit and underground mines, some extending over 2 kilometers straight down into the shattered crust. The immense volume of rock removed has fundamentally altered local hydrology, forcing ongoing drainage management, water treatment operations, and structural monitoring of deep underground shafts by major mining operators like Vale Canada and Glencore.
The environmental footprint of early smelters
which released massive amounts of sulfur dioxide and heavy metal dust across the surrounding watershed, triggered severe acidification of thousands of nearby lakes during the mid-20th century. Reclaiming that damaged landscape, often called the re-greening of Sudbury, has involved decades of work, planting over 10 million trees and spreading thousands of tons of crushed limestone across surrounding hillsides to neutralize acidic soils, an effort coordinated between local authorities, Laurentian University, and industry partners. Today, while forests have returned to the basin, the legacy of tailings management ponds, deep underground voids, and active mineral processing facilities remains a permanent fixture of regional infrastructure. Beyond the physical footprint, the scientific recognition of Sudbury as an impact crater changed global mineral exploration. Geologists no longer restrict their search for critical metals like nickel and copper to conventional volcanic arcs. Instead, they analyze ancient impact structures worldwide, applying shock metamorphism indicators to trace hidden mineral concentrations. For the residents who drive past the rocky outcrops along Highway 17 every day, the massive bowl-like basin forms the literal floor of their daily lives, a geographic feature where houses, farms, and roads sit inside the eroded basin of a prehistoric cosmic catastrophe. Yet, as significant as the Sudbury Basin is to Canada's economic and geological landscape, it is not the only place where a misread line on a map or an overlooked natural phenomenon has reshaped our understanding of the country. When you stand back and look at the whole expanse of northern Ontario, the final realization is not simply that a vast ore body was hidden underground, but that the true nature of the structure was masked by an assumption about how Earth processes operate. What kept the Sudbury Basin misunderstood for 80 years was not a lack of physical evidence, a missing map sheet, or incomplete assay reports. It was a conceptual framework that insisted a large, circular ring of igneous rock in the Canadian Shield had to be an ancient volcano. The rock was sitting in plain sight, mapped by field crews and drilled by mining companies. Yet the official record assigned it to the wrong category, because science had not yet built a category for hypervelocity extraterrestrial impacts. Even today, significant questions remain unresolved. Geophysicists and geochemists continue to debate the exact trajectory, speed, and precise composition of the bolide that struck the shield nearly 2 billion years ago, as well as the exact proportion of target rock that was vaporized versus melted. Modern deep seismic imaging and high-resolution gravity modeling continue to refine our understanding of the deep basin geometry, probing structural boundaries that extend kilometers beneath the current operating mines. Meanwhile, ongoing erosion and glacial rebound slowly alter the surface, reminding us that the physical land is never entirely static. The map sheets published by Natural Resources Canada look clean, definitive, and complete, but the ground beneath them is always holding a deeper story than the ink reveals. Which landscape or forgotten geographical detail in your own province or territory has always struck you as unusual? Tell us about it in the comments below, and consider subscribing to stay connected with our ongoing exploration of Canada's